We're going to be starting with our good old periodic table. And again, we're going to keep going back to periodic table. Now, I want to remind everyone that there are two categories of electrons: core electrons, valence electrons. And again, the total chemistry of the atom is determined by its valence only electrons. Okay, valence only. So for example, we looked at sodium. Sodium has 11 electrons in total. Some are core, some are valence. To count valence, you just start from the left on the row it's on and count over. So how many do we count over for sodium? 1. That means it has 1 valence electron. The remaining electrons are core. Okay. We've already talked about 4 groups on the periodic table you ought to know. You have the alkali metals, the alkali earth metals, halogens, and noble gases. What goes across are called periods. Or shells. Now, what I'm going to talk about today, shells are the key word there, not necessarily periods. Okay. Within the shells are subshells. That means each period or each shell is subdivided into subshells. And it depends on which one we're talking about, how many there are. Okay, so this is shell 1, and there is 1 subshell there. Shell number 2, there are 2 subshells. Okay, the subshell are named S. And that accounts for both those columns, and P. On shell number 3, there's the same as shell number 2. We have S's and P's. Shell number 4, and that's as far as you're going to go on the periodic table as far as electronic configuration goes. On shell 4, there are S's and D's. And as we keep going down, we're going to finally get to down here. These are the F's. So there's S, P, D, and F. We're not going to do any F's in this class. In 1A, you will definitely be doing everything. Okay, so let's look at sodium again. Okay, sodium has 1 valence electron, 10 cores. Now we have to account for all 11 electrons with electronic configuration notation. Okay, so if we look at sodium over here, it has got electrons in the 1 shell, in the 2 shell, and the 3 shell. Okay, that's because all the electrons above it are core electrons. And those core electrons occupy the 1s shell, the 2s shell, the 2p shell, and the 3s shell. Okay, we have to account for all the electrons above it. So the way we designate that is we go shell 1, subshell S, and how many electrons are in that? 2. Okay, we know it can only hold 2 because we can't fit any more in shell number 1 as 2 electrons. 1, 2. So we're done with shell 1 now. Now we need to go to shell 2. Okay, in shell 2, we've got, so this is the shell. That's the subshell. And that's the number of electrons in the subshell. So there are 3 parts to every one of these. What's the main shell? What's the subshell? And how many electrons are in that subshell? Okay, on shell number 2 now. Okay, we've got electrons in the S's here. And there are 2 of them. Now, as we go across, we run into the P subshell now. That's in shell 2, subshell P, and we have 1, 2, 3, 4, 5, 6 electrons there. Okay, now we're going to go to shell 3, and that's where sodium is located. Shell number 3. How far in is sodium on the S subshell? 1 in, that's right. So that means on the S, we have 1 electron there. Okay, so that's the electronic configuration for sodium. The 1s2, 2s2, 2p6, 3s1. Now, think about uranium. Uranium has 92 electrons. That's a whole bunch of electrons to account for. Glenn, did you have a question? It has to do with the way the electrons congregate around the atom. Okay. So we have S areas, P areas, D areas, and F areas. So are those just designations for how far out it is? How far out, and also how they're organized. What kind of shape. Okay. Now, this is not a Bohr model. Bohr said the atom has planetary-like orbits around the nucleus. That's 150 years old, wrong model. We're using the quantum mechanical model now, which is more of a statistical treatment. So it can predict shapes, but not necessarily where exactly the electrons are, just the probability of finding an electron in a certain area around the nucleus. It's kind of an obtuse concept, but that's where we are. Okay. Now, we do have orbitals in the quantum mechanical model. Bohr's model, we have orbits. In the quantum mechanical model, we have orbitals. And remember in Lewis dot structures, how many electrons were in a bond? Yeah, 2. And that corresponds to an orbital of 2. No more than 2. So how many orbitals are in the S subshell? One. 2 electrons, 1 orbital. An orbital or a bond can hold only 2 electrons, just like we did the Lewis dot structure, connecting the singletons together. Okay, P subblock or P subshell. How many orbitals do we have there? There's 6 places. Now this is tough math. 6 divided by 2, 3. We have 3 orbitals in the P's, just like you said. Okay, and then we get back to S. Now, The S is half full because it can take 2 electrons. There's only 1 there. It's half full. Okay, so let's do some more of these. Get some more practice under our belts here. Okay, let's do carbon. Oh, one other thing. The superscripts have to add up to 11. So we have 2, 4, 6 is 10, 1's 11. So if those don't add up to the atomic number, something's wrong. Because we have to account for all 11 electrons. Okay, carbon. How many total electrons does carbon have? It has 4 valence. How many total? Who said 6? Okay. And you said there were 4 valence electrons, right? Okay. So you have 4 valence, 2 core. And I'm going to take those valence electrons and core electrons now and give them these S and P designators. Okay, so carbon is located here. Okay, so what shell is it in? 2. What subshell is it in? P. So our final designator is going to be 2P. And how far into the P is it? 2. So it's going to be our final number. It's going to be 2P2. All right. So let's start with the core electrons first. And I know this is cryptic. Yeah. We're just accounting, it's doing like an inventory, accounting for all the electrons. And we're doing them 2 at a time in the orbitals. In a minute, I'm going to actually have little orbital indicators. Okay, so carbon. Okay, first of all, we need to account for all the shell 1 electrons. So that's going to be okay. Now we have to account for the shell 2 electrons. Now that's not a full shell. A full shell would be like neon over here. So we're partially through shell number 2 into the P's. So how many S electrons are there in that shell number 2? 2. What about the P's? How far are we into the P's? 2. Okay, so let's add the electrons up at the top. 2, 4, 6. What's the atomic number for carbon? 6. So we accounted for all the electrons. Okay, all right. Let's do some more here. Let's do neon. Okay, neon is right here. So neon is also in shell number 2. And its atomic number is 10. So we're going to have 10 electrons identified. Okay, so that's we have 2 in the 1s shell, 2 in the 2s shell. And how far into the P's are we? 6. Okay, so 6 plus 2 is 10. That's the atomic number for neon. Now, something important. Notice the shell is full. You can't put any more electrons in shell number 2. And the reason for that is it's reached its most stable configuration. Most stable configuration is when the whole shell is full. That's why the noble gases on the far right are so stable, is because their shell is totally full. Okay, and that's a big driving force when we start talking about ionic bonding and covalent bonding, because what those bonds do is fill up that shell so it's a full shell. It's called isoelectric. Isoelectric means the same. Isoelectric means electrons. Same electrons as a noble gas. So it's isoelectric with the noble gas. Same number of electrons. Super stable. Okay, so let's do, so far, I know this is very cryptic. I've been doing this for many decades, and every student I showed this to the first time, they go, huh? Okay, so I get it. I understand. But this is how we predict the stability of both ions and neutral atoms by looking at their electronic configuration. We look to see if we have full subshells, full shells, or not full subshells. And before I go on, I want to actually show you what the orbitals are going to look like. So we have one orbital in the S's, one orbital in the S's, and we've already said there were 3 orbitals in the P's. Remember, the orbital can only have 2 electrons. Okay, so let's now represent the orbital with electrons in them. Okay, so the 1s are going to be 2 electrons. And notice I'm making the arrows opposite because electrons have a magnetic component. And if you've ever played with magnets, you know there's one way where the magnets stick together, the other way they repel. It's more stable when they stick together. That's why the arrow directions are opposite. So the poles of the magnetic components of the electrons want to stick together. Okay, 2s, 2 electrons. Now the p's. Now this is the way, if there's multiple orbitals in a subshell, this is the way they're filled. We do one at a time first. So we're going to go 1, 2, 3. We have 3 more to go. Now we pair them up afterwards. So that's the orbital representation of neon. Okay, so on the test, if I ask you for the orbital representation, you can do it as squares or circles, whatever you like drawing more. Some books do one, some books do another. It doesn't really matter. You just have to represent an orbital. Okay, so if there's more than 2 electrons, like S block, you're gonna have to fill it out one at a time. Then start pairing them up. Okay, so that's neon. But the electronic configuration, what you need to do first, before you can do the orbital. Jack, what problem was wrong in the homework? There's one error on the homework I assigned that the book is wrong. It involves the configuration for nitrogen. Yeah. It was nitrogen, yeah. So let's do nitrogen before we go on, and I'll show you the book's error versus what's really correct. Okay, so nitrogen. Look up nitrogen. Nitrogen's over here next to carbon. It has 7 total electrons. So the atomic number is 7. And there are 5 valence, 2 core. So 2 in the shell number 1, 2 in the subshell S and shell number 2. And how far into the P's are we going to go? 3. Okay, so let's do the orbital representation now. So we have to represent the S's with a pair in there. And then we're going to fill out the 3 electrons, 1 per orbital until they start pairing up. And this is the correct one. The book says, oops. Isn't that how the book did it? Yeah. So this is wrong. Okay. So when you're doing problem 59, just okay. You always fill up the shells on the left before you do the shells on the right. And why do we have to do that? What is the main answer to all my problems in this class? Stability reasons. Yeah. The ones on the left are more stable, so they fill first. So we go from left to right in decreasing stability as you go across the shell. Okay, so let's do some more here. Now let's do, let's get into row or shell number 4. Let's do, let's do gallium. Now notice gallium is in shell number 4. Shell number 4, and it's located in the P block of shell number 4. So it's the same old thing. I want you to notice a pattern here. We start with the 1s, and we go to the 2s, then we go to the 3s, then we go to the 4s, and gallium is in, oh, excuse me, let me back up. It is gallium, right? Yeah, okay. Now, what have I not accounted for? The D block. That's right, these guys here. So as we go across to get to gallium, we encounter the Ds. So that has to be in our electronic configuration. The problem with the Ds is they're not in shell 4, they're in shell 3. This is what's weird about the Ds. So I usually tell people, if you want to remember the Ds, think of the Ds as dumbed down by 1. So when we account for those D electrons, they're going to be in shell number 3. and they're going to go right here. So we need to move that 4p over. Okay, and how far across are the D's? Okay, if we count, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're going to go all the way across before we get into the P block. So that's the configuration for gallium. Now let's do the orbital representation for gallium. Now the D block can hold 10 electrons. 10 divided by 2 is 5. That's why there are 5 orbitals for the Ds. Notice how I fill all of them first with 1 electron, then we pair them up afterwards. And we're 1 into the P block. So that's the orbital representation for gallium. Now again, think about uranium. We have to count for 92 electrons in uranium. Now, the deal is, remember there are 2 kinds of electrons, core and valence. Valence electrons determines the chemistry, not the core electrons. So what we usually do is abbreviate the core electrons, since they don't do anything anyway. And you abbreviate the core electrons by using the nearest noble gas. So let's go back up here to, we did with nitrogen. What's the nearest noble gas to nitrogen? Helium. So we can represent the 1s2 and just put an H there. Helium in square brackets is the same as 1s2. Now, it's not much of a shortcut when we're talking about, look at gallium now. What's the nearest noble gas to gallium? Argon. We go up 1 and to the right, argon. So the higher elements, it's really a time saver to represent the core electrons as a noble gas. Now you may do it either way, it's fine with me. But on a test, if I ask you, for example, how many electrons does that represent? Okay, then you would then go to the periodic table, look at the atomic number for argon, which is 18. So that represents 18 core electrons. And these represent the valence electrons. Now we're only going to go to shell number 4. When you go into 1A or 3A, you're going to be doing the whole shebang. Let me show you what, don't write this down, okay? I'm going to show you what uranium looks like. I have to count for 92 electrons. I'm running out of space. Okay, so that's the configuration for uranium. Or the abbreviated one, what's the nearest noble gas to uranium? Uranium is located right here. Yeah. A big difference. So that's a 1A kind of problem. So the more complicated these get, it's more important to write the abbreviated one. Because again, the abbreviation stands for the core electrons that don't do chemistry. Only the valence electrons do the chemistry. F's are 2 down. Okay, so you're going 6s2, 4f, and then back to D's, and then P's. There are 2 periodic tables running around. It has to do this spot right here. Right. Right. I know, but there's bottom line is that's why we're not doing F still 1A. Because in 1947 at the American Chemical Society meeting in Brussels, a whole bunch of people decided that the actinides and lanthanides don't belong in F, only some of them. And they stomped out of the conference. And that's the derivation of the 2 periodic tables. There's a real, kind of a brat syndrome. They just couldn't take that someone else could disagree with them. All right, anyway, the bottom line is you have to account for all those electrons. If we counted the superscripts on these, we'd end up at 92. And then we'd have associated orbitals, which would be kind of wild as well. Okay, so let's now do some more simple ones. Let's do iron. Definitely write this down though. Okay, iron. Got to find iron on the periodic table. The iron is right here. That means it's smack in the D subshell. So that means we're gonna have to count for some D electrons. So it's in the, going to be having 4 S's and D's, and then the 3 S's and 3 P's and 3 S's and the 2's and the 1's. We have to count for all those. Okay, so and how far in is iron? Iron is 5N. Okay, so that's electronic configuration for iron. And what's the closest noble gas to iron? Going to be argon. What? Six N. Okay, so that's the abbreviated one. So let's look at the orbital representation for that. So we've got, let's just do the valence orbitals here. So we have 1 orbital for S's, and then 5 orbitals for the D's. Okay, so we have 2 in the S block, 2 in the S subshell, I should say, and we have 6 in the D subshell. So that would be the orbital representation for iron. Now, knowing this is important in predicting what ions form. Okay, so let's look at shell stabilities. Absolutely, the most stable shell is going to be a full shell, like the noble gases. Next is a full subshell. Next is a half full subshell. And then nothing in particular is stable. Okay, now you need to know these. So tell me this guy here. This is what, iron. Okay, so now this only applies to the valence electrons. In fact, let's even mark that down. Okay, so for iron, that's the valence shell electronic configuration. And here's the orbital representation. So let's look at these rules here on valence shell stabilities. Okay, is number 1 fulfilled? Is it a full shell? No, because it's got to go all the way across to be a noble gas to be a full shell. What about a full subshell? Okay, we've got 1. That's a subshell that's full. The capacity of S is 2 electrons. We have 2 electrons in it. What about the D's here? That's nothing. That's a partial nothing. So that's not particularly stable. A half subshell would mean we'd have to lose 1 electron. And that would be this one here. And then we would achieve a half full subshell. Guess what ion iron likes to make? What? If we lose 4 electrons, we're still going to be in the nothing. How many electrons do we need to lose? 1. If we lose 1, look what happens. Now we have a half full subshell. So iron likes to lose 1 electron. When it loses 1 electron, it becomes more stable. Why? Because it's gone from number 4, nothing, to now a half full subshell. So you always see a +1 ion for iron. So that's why these configurations really help trying to predict ions. Because if you lose or gain electrons and you go up the table here to more stable configuration, that's the driving force for it to happen. Okay. Let's look at all right, why don't everyone write the electronic configuration for calcium? Calcium is in shell number 4, 2 over. You can do the abbreviated one or the full one. Doing great so far. Yep. Yep. Exactly. I'll see you then. Yep. I have not gotten it yet on your link. I haven't grabbed it yet. Okay. Yeah, I just wanted, because you asked me in an email or message, and I haven't got it. Yeah.
Oh.
Yeah, you sent me the link. I just haven't acquired it yet. So. Okay, so I want you now to predict. Let me make sure everyone's on the same page here. So what ion do you think calcium would form? Now, right now we're sitting at a full half shell, so that's not too bad. But what can we do to make an ion, and number two, make it super stable? What's the most stable? Full shell, right? Is there any way we can manipulate that guy to make it a full shell? Lose two, even though it's a full subshell, but it can be made better by losing two, and then it's a full shell. That's why calcium forms a +2 cation. And once we lose 2 electrons, it's a full shell now, super stable. Okay, so again, it helps us predict, and everyone in that group, the alkali earth metals, is all S2s. All are S2s. So they're all going to lose 2 for exactly the same reason. Say again? What is it? It's electronic configuration. Electronic meaning electrons, and how are they configured? Okay, so let's look at some more. All right, let's look at sulfur. Go and do electronic configuration for sulfur. No, the S can only hold 2. And you know how you don't have to even memorize it, just count. Only 2 there. You have to know it's in this block though. Same with the P's. 1, 2, 3, 4, 5, 6. Right? The P's, D's are 1, 2, 3, 4, up to 10. Yeah, and shell 3, a big 3, and how far in? Mhm. Yeah. Okay, so S is in shell number 3. What's the nearest noble gas, right? Neon. How far into the P's is sulfur? 4. So that's what it looks like for sulfur. Now, next question is going to be, how can we improve the stability of sulfur the way it sits? Keeping those stability rules in mind. We could lose a bunch of electrons or gain 2. What do you think is easier? Make it much more stable. Okay. And gaining 2 versus losing how many?
1.
Losing 1. Yeah. So which is more stable, a full subshell or a half full subshell? Full, yeah. So that's where we're going to gain 2. So it's going to be isoelectric now with neon. It should be argon. So it's easier on the gaining or losing the smaller number of electrons. And sometimes you say, I want to lose 10 electrons. Well, that's not going to happen.
When it comes to finding the nearest noble gas, do you always go up and then over, or?
You go up and over when you're doing the abbreviation,
Okay.
but when we're looking at stabilities of an
It's
ion,
just-
yeah. So if we gain 2 electrons, that means it ends up being isoelectric argon.
Okay.
If we
When we're writing
lost,
out the electronic configuration.
Yeah. if we lost all of these, then it would be like neon, but that's a whole bunch to lose.
Yeah, got
Nature just doesn't like to do that. Okay, now this just takes a bunch of practice. So that's what I wanted to cover tonight. Next week, we're going to talk about naming. That's one of the big weak spots in Chem 1A students, naming binary compounds. Also, dimensional analysis, another weak spot. Those 2 biggies. Okay, so we are done for tonight. And let's head over to lab and do some valence shell electron pair repulsion. Okay.